only single. But what happens if the energy source is more than one? Then the Ohm's law cannot be preferred. Then we are using the Kirchhoff's law. So the French German scientist gives the best equation which directly used or to solve the logic of that kind of circuit, that's a using of the Kirchhoff's law. It gives us the basic two laws, that is the Kirchhoff's current law and Kirchhoff's voltage law. It's also known as the Kirchhoff's first law and the second law. First law is also, we said that the Kirchhoff's current law, it is also known as the junction rule. Kirchhoff's voltage law, it is also known as a closed loop rule. So that is the first law and that's a second law. Now just we go through the junction rule, or it's a first law. What exactly the Kirchhoff's current law or the Kirchhoff's first law says, or the junction rule? At any node or the junction in an electrical circuit, the sum of currents flowing into that node is equal to the sum of current flowing out of that node. Or ultimately we can say that the algebraic sum of the current in a network of conductors meeting at a node point is 0. See the equation, that is a sigma I in, that means number of input current are always equal to the number of output current with respect to any node. See, there is an example, figure A, figure B and figure C. Here this is a node where we can see that the current IA which is enter, current IB is flowing towards that node. Taking the figure B, that the current IA enter, current BIN enter, current IC also enter, but the current ID is flowing towards that node. So ultimately what happens, actually if we want to define with this example with the equation, then we can see that the current IA enters while current IB exit. So we take the positive sign if the current is enter towards the node, and if the current is exit to the node, then we take the sign as a negative. So we can say that the IA minus IB equals to 0 for the figure A. Then for the figure B, we can say that the IA plus IB plus IC, because all three currents are entering to the nodes, so they all are considered as a positive. But I minus ID, we take the minus ID because ID is the flowing toward the or out of the node. As per the figure C, that is current IA is enters, it means plus IA, IB also enters, that means plus IB, but IC and ID are out, current flowing toward the node, it means they both are taken as a negative. So it means IA plus IB minus IC minus ID equal to 0. C. We can also write the equation like that, IA equals to IB. For figure B, we can write that IA plus IB plus IC equal to ID, and for figure C, we can write that the IA plus IB equal to IC plus ID. Now the Kirchhoff's current law, there is one example here. Just if we want to find out the what the value of the current toward the resistance R3. See the figure. There is one resistance R1, R2, R3 and the EMF, that is E. Here we can see that the 10 ohm resistance used, so the current is 10 ampere current will be enter, and the 4 ampere current flowing toward the resistor, that is of node A or point A, that's the point B, and we have to find out the value of the current in the point B. So we, according to the KCL, the current entering into the node A, that is 10A, which is equal to the current outward toward the node A, that is 4 ampere. So 10A minus 4A equals to 6 ampere. So overall current will be flowing toward the resistor R3, that is the 6 ampere. Now that 6 ampere is also adding to the resistance R2. So ultimately at the node B, the total value of the current is 4 ampere plus 6 ampere, that is a 10 ampere. So we can just easily, using the Kirchhoff's current law or the first law or the junction rule, we can easily find out the value of the current at any node point. Now the second law of the Kirchhoff's, that is the closed loop rule. It states that the algebraic sum of the voltage, all the voltage around the closed loop is always equals to 0. The equation will be like that, sigma delta V closed loop equals to 0. Same as the inward current to the outward currents are also equal. The second law state that the overall voltage toward the node is also 0. An example of a circuit with the electron flowing in the circuit, it will be shown here. There's a figure that the point D, A, B, C and D, 4 node points, resistance R2, resistance R1 and the current will be flow toward the negative terminal of the battery, that is flowing to the negative toward the point A through the resistance R1 to B and around that point C, R2 and point D. So this is the path of electron or the current flowing in the circuit. Now just find out the value of the voltage at any given circuit. There is one circuit. Also we can consider it the positive terminal of the battery, negative terminal of the battery. Just we have to find out the value of the EMF. If we have the different values of the voltage drop, like 125 across the resistance R3, 50 voltage across the resistance R2 and 25 voltage across the R1, then using the Kirchhoff's voltage law, we just go through the we just find out the value of the EMF. So friends, here what happens, if the negative terminals is leaving the electrons, then it considered as a negative. So here voltage drop across the R1, R2 and R3 all are taken as a negative, and here the EMF is given the sign as a positive to negative, so it means it rises. So EMF E is taken as a positive. So according to the equation of KVL, we can say that E minus 25 minus 50 volt minus 125 equals to 0. This is the sigma delta V equals to 0 through that equation. So we can find out the E equals to 200 volt. Just go through one example. Kirchhoff gives the best relation when the source of EMFs are very large. See the figure A and figure B. These are the two circuits. If you want to reduce the circuits A and B, then you can easily use the circuit A as a series circuit which has the one source of EMF, circuit B as a parallel circuit, and both the circuits can be solved with using the Ohm's law. But what happens if the circuit will look like this circuit C, which has the more than one EMF source? Then it cannot be that's a bridge circuit cannot be solved with using the Ohm's law. Then we use the Kirchhoff's law. So as the Kirchhoff's give the two laws, Kirchhoff's current law and the Kirchhoff's voltage law, we can easily find out any current or any voltage to the node. Just go through that. This is the bridge circuit, and we just take one example. It's a bridge circuit. It has two nodes, node A and the node B. What exactly the node is, or these are the junction. The conducting, when the two or more than two conductors are meet at a point, it is known as a node or the junctions. This is a loop, any closed conducting path working as a loop. So here it's a loop. These are the nodes. All are wires conducting, known as a loop. So according to the Kirchhoff's current law, or we already learned that the sigma I in equals to sigma I out, both are equal to. See the figure. Here what happened? The I1 enter, I2 leave, I3 enter, I4 leave and I5 enter at the node O. So according to the Kirchhoff's current law, the inward current taken as a positive sign and the outward current taken as a negative sign. So here we can write that the I1 plus I3 plus I5 equal to I2 plus I4. Or we can also write that I1 minus I2 plus I3 minus I4 plus I5. See here, you can write like that. Both the ways the answer is true at any node. So this is the all the fundamental concepts of electricity. Thank you.